So let's get started. We have a plan to halve the cost per kilowatt hour. And we're going to go through that plan with you today, step by step, and build up how we get to these goals and how we accelerate this transition and make our vehicles and our grid batteries more affordable. We came up with tabless architecture that maybe you've heard about. Basically removes the thermal problem from the equation and allows us to go to the absolute lowest cost form factor and the simplest manufacturing process. And this is what we mean when we talk about tabless. We basically took the existing foils, laser patterned them, and enabled dozens of connections into the active material through this shingled spiral you can see. With simpler manufacturing, fewer parts, 50 millimeter versus 250 millimeter electrical path length, which is how we get all the thermal benefits.
Yeah, this is important to appreciate. Like basically the distance that electron has to travel, is just much less. So you actually have a shorter path length in a large tabless cell than you have in the smaller cell with tabs. This is a big deal. So even though the cell is bigger, it actually has more power. The power to weight ratio is actually better than the smaller cell with tabs.
As you make cells larger, in fact, supercharging and thermals in general become really challenging as you make bigger cells. And this was the challenge that our team set our sights on to overcome. So as you can see, we kind of swept the key figures of merit, how much we can reduce the cost and how much vehicle range increases as we change the outer diameter of the cell. We found a sweet spot somewhere around 46 millimeters. And so when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase just form factor alone. I want to stress, this is not just a concept or a rendering. We are starting to ramp up manufacturing of these cells at our pilot 10 gigawatt hour production facility just around the corner.
Yeah. So
let's stack up everything we just saw at the cell level. So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. One of the most important processes is where it all begins, the wet process of the electrode coating. You've got mixing where the powders are mixed with either a water or a solvents for the cathode. That mix then goes into a large coat and dry oven. Wouldn't it be great if we could skip that solvent step, which is one of those dig a ditch and then fill it kind of things where you put the solvent in and then take it out and recycle it, and just go straight to dry mix to coat. And that's what the dry process really is about. You can see it here on a benchtop. Literally powder into film. As simple as that.
I would not say this is like completely in the bag. It's still a lot of work to do, and as you go from like benchtop to lab to pilot to volume production, there are actually major issues that you encounter at every level.
So you can see the motivation: a 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment. Let's talk a little bit about assembly, which is next. We were able to get to the point where we can implement assembly lines, one line, 20 gigawatt hours, 7 times increase in output per line.
Not every company will be great at manufacturing. Tesla will be absolutely head and shoulders above anyone else in manufacturing. That is our goal.
Now let's talk about formation. 86% reduction in formation investment, 75% reduction in footprint.
So essentially, what this translates to, based on what we know today, is about a 75% reduction in the investment per kilowatt hour or gigawatt hour. It's just basically 4 times better than the current state of the art to the best of our knowledge.
Simpler accelerates terawatt hour scale, and that's what we need to do to accelerate our mission.
This is just talking about Tesla internal cell production. As I tweeted out earlier, we will continue to use our cell suppliers, Panasonic and LG and CATL. So this is 100 gigawatt hours supplemental to what we buy from suppliers. Essentially, this does like reduce our weighted average cost of a cell because it allows us to make a lot more cars and a lot more stationary storage. And then long term, expecting to make on the order of 3,000 gigawatt hours or 3 terawatt hours per year. I think I think we've got a good chance of achieving this actually before 2030, but I'm highly confident that we could do it by 2030.
And not only is all of that manufacturing innovation fantastic for enabling scale, it's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level. So we have a manufacturing system, we've got a cell design. What are the active materials we're going to put in that cell design? Let's talk about the anode first. Let's talk about silicon. It's the most abundant element in the Earth's crust after oxygen. And it happens to store 9 times more lithium than graphite, which is the typical anode material in lithium-ion batteries today. Challenge with silicon is that it expands 4x when fully charged with lithium. And basically, all of that expansion stress on the particles start cracking, they start electrically isolating, you lose capacity, the energy retention of the battery starts to fade. And current approaches to solve this, which exist, I mean, we have silicon in the cars that you're all in right now, are involved highly engineered, expensive materials. What we're proposing is a step change in capability and a step change in cost. And what that really is to just go to the raw metallurgical silicon itself. Don't engineer the base metal. Just start with that and design for it to expand in how you think of the particle in the electrode design and how you coat it. With this silicon, and the anode costs $1.20 a kilowatt hour.
Yeah.
By leveraging this silicon to its potential, we can increase the range of our vehicles by an additional 20%, just this improvement.
Yeah, it gets cheaper and longer range.
And when we take that anode cost reduction, we're looking at another 5% dollar per kilowatt hour reduction at the battery pack level. Let's talk about cathodes. I think people are always talking about like, oh, what's the cathode going to be? Is it NCA or whatever? You know, the thing to consider is just fundamentally what the nickel, the metals are capable of. And that's what we have on the chart here. Dollar per kilowatt hour cathode of just the metal using just LME, you know, London Metal Exchange prices, versus the energy density of just the cathode. And you can see nickel is the cheapest and the highest energy density. And that's why increasing nickel is a goal of ours and really everybody's in the battery industry. But one of the reasons why cobalt is even used at all is because it is a very stable bookshelf. And the challenge with going to pure nickel is stabilizing that bookshelf with only nickel. And that's what we've been working on with our high nickel cathode development, which has 0 cobalt in it. Leveraging novel coatings and dopants, we can get a 15% reduction in cathode dollar per kilowatt hour.
Yeah. I think we need to have a kind of a 3-tiered approach to batteries. So starting with iron, that's kind of like a medium range, and then nickel manganese as sort of a medium plus, intermediate, and then a high nickel for long range applications like Cybertruck and the semi. It's relatively straightforward to do a cathode that's 2/3 nickel, 1/3 manganese, which would then allow us to make 50% more cell volume with the same amount of nickel.
35% of the cathode dollar per kilowatt hour is just in transferring it into its final form. And so we see that as a big target, and we decided to take that on. And that's what we're proposing here with our process. As you can see, a whole lot less is going on here. We get rid of the intermediate, metal, water, final product cathode, recirculate the water, no wastewater at all. And when you summarize all of that, it's a 66% reduction in CAPEX investment, a 76% reduction in process cost, and 0 wastewater. Much more scalable solution.
Yeah.
Obviously, we're going to go and start building our own cathode facility in North America and leveraging all of the North American resources that exist for nickel and lithium. And just doing that, just localizing our cathode supply chain and production, we can reduce miles traveled by all the materials that end up in the cathode by 80%, which is huge for cost.
Cathode production would be part of the Tesla cell production plant. So it would just be, basically, raw materials coming from the mine, and from raw materials in the mine, out comes a battery.
The way the lithium ends up in the cell is through the cathode, so then we should obviously on-site lithium conversion as well, which is what we will do using a new process that we're going to pioneer. That's a sulfate-free process again, skip the intermediate. 33% reduction in lithium cost, 100% electric facility co-located with the cathode plant.
It's important to note that there is a massive amount of lithium on Earth.
Yeah.
So lithium is not like oil. There's a massive amount of it pretty much everywhere. Every vehicle in the United States can be converted to electric using only lithium that is available in the United States. We can actually use table salt, sodium chloride, to basically extract the lithium from the ore.
All of the benefits that you just saw are added to this benefit of a 12% reduction in dollars per kilowatt hour at the battery pack level. Almost at our halve the cost goal, but there's one more section. Take it away, Elon.
Great. So it starts with having a single piece casting, or a single piece casting for the front body and the rear body. And in order to do this, we commissioned the largest casting machine that has ever been made. And it's currently working just over the road at our Fremont plant. We have it's pretty sweet. Currently making the entire rear section of the car as a single piece, high pressure die cast aluminum. And in order to do this, we actually had to develop our own alloy because we wanted a high strength casting alloy that did not require coatings or heat treatment. So you're basically making the front and rear of the car as a single piece, then interfaces to what we call the structural battery, where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure. So this is really quite profound. Effectively, the non-cell portion of the battery has negative mass. We save more mass in the rest of the vehicle than the non-cell portion of the battery. It also allows us to pack the cells more densely because we do not have intermediate structure in the battery pack. Instead of having just a filler that is a flame retardant, which is currently what is in the 3NY battery packs, we have a filler that is a structural adhesive, as well as flame retardant. So it effectively glues the cells to the top and bottom sheet. And this allows you to do shear transfer between the upper and lower sheet. Just like if you have like a Formula One craft or like a racing boat and you have carbon fiber face sheets and say aluminum honeycomb between them, this gives you incredible stiffness. And it's really the way that any super fast thing works is you create basically a honeycomb sandwich with two face sheets. We can actually use the steel shell case of the battery to transfer shear from the upper and lower face sheet, which makes for an incredibly stiff structure, even stiffer than a regular car. The volumetric efficiency of the structural pack is much better than a non-structural pack, and we actually bring the cells closer to the center, and because they're closer to the center, it reduces the probability of a side impact potentially contacting the cells, because it has to go, any kind of side impact has to go further in order to reach the cells. If you can bring things closer to the center, you reduce the polar moment of inertia, and that means the car maneuvers better. It just feels better. You don't know why, but it just feels more agile. It's really cool. This is really major. Like I said, so 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts.
And it's not just at the product level a better product, but in the factory, it's a massive simplification. So we're looking at over 50% reduction in investment per gigawatt hour, 35% reduction in floor space, and we'll continue to improve that as we make the vehicle factory of the future. In addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah.
Range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery pack level, and a 69% reduction in investment per gigawatt hour, which is the true enabler when we talk back about how do we achieve this scale problem here.
Yeah. What this enables us to do is achieve a new trajectory in the reduction of cell cost. And now, to be clear, it will take us probably a year to 18 months to start realizing these advantages, and probably to fully realize the advantages, probably it's about 3 years or thereabouts. So the long-term scaling of Tesla and the sustainable energy products that we make will be massively increased. I mean, long-term, we want to try to replace about, at least 1% of the total vehicle fleet on Earth, which is about 2 billion vehicles. So long term, we want to try to make about 20 million vehicles a year. What does this mean for our future products? We're confident that long term we can design and manufacture a compelling $25,000 electric vehicle. So we have and extreme performance and range, and we should probably talk about the Model S Plaid. What about that?